Now you are going to learn the implementation of the UVM environment development for the interconnect DUT. So before starting, just keep in mind that this is the overall picture of the DUT that you are going to implement a verification environment. It got two interfaces, two set of interfaces, two set of AXI interfaces coming from two AXI masters, and one OCP interface which is going to the OCP slave. So the interconnect is actually a router which will route the transaction from these two set of interfaces to the single OCP interface. Also, every AXI interface contains 5 different channels: a write address, a write data and write response, and a read address and a read data channels. So now the basic restriction here for this masters to send transactions in this interface is that the AXI master 1 will send all the transactions with ID from 0 to 7, and the AXI master 2 will send the transaction from ID 8 to 15. So you know the width of the ID field in every AXI interface is bit 3 down to 0. Thus, the total bit we are dividing equally between two masters. The first master will send transaction from 0 to 7 with ID, and the same way second transaction with ID 7 to 8 to 15. And using this ID, the interconnect will identify the responses coming back from the slave, and it will route them appropriately. Now you are going to see the code implementation for the same. I have implemented this in EDA Playground, the online simulation tool. It's a free tool available. You can also try this. And here in the right hand side, you will write the design content, and in the left hand side, you will write the verification contents. And I'm not going to explain the design parts here. We will come back to the top level design, which is the DUT, at the point where we are discussing the top level test bench module. Now you are going to start the implementation one by one. We will start with transaction definition. So we have to define transactions for representing AXI and OCP interface transactions. The general definition of every UVM classes is explained in detail in the previous session, so those concepts will not be repeated in the working session. And here the AXI transaction is a class which is extending from the UVM sequence item, and it is registered with the UVM object util. And these are the members in the AXI transactions. All the members are defined as random by using the Systemverilog keyword rand. And the first member is the read write type, which will say that it's a read or write, and this is an enumeration defined in the general definition, the design part. And all other fields, the ID, length, address, data are of same width, which are corresponding to the parameters in the AXI interface. So ID is individual ID, and for the first master it will be sending with IDs from 0 to 7, and the second master will be sending transactions with IDs 8 to 15. And the new function, we have already described how to define the new function in the transaction. And also the constraints are added, which are default constraints. So always the length should be greater than 1, and the data dot size will be equal to length. So if it's a length is 1, it will have only one data member. In the do copy function, the shallow copy of the object is defined by copying the individual members one by one, and also you can see that the data array, the data of I are copied individually to make that it's complying a shallow copy. And before starting copy, we can just make a typecast and see that this is the argument passed to the do copy is of type as expected, which is AXI transaction. And in the convert to string function, we are implementing the string conversion of the individual fields. So the Systemverilog $s format is used to concatenate strings with their appropriate values, which are the name, address, ID, length, etc. And also all the data members are appended here. And this function will return the printable or the debuggable message when it is called. And also you can implement other functions like do compare, do record, do pack, and do unpack. But these functions might not be needed in all the cases. And in the same way, the OCP transaction is extending from the UVM sequence item. After the factory registration, these are the individual fields in the OCP transaction. The first field is the OCP command. Again, it's a type def in the general definition. So you have to add explicit type def for this. So you can see this OCP, these are the commands. So this is complying with the OCP protocol definition. And out of which we'll be interested or we'll be implementing only write and read transactions in our environment. Also, other members like ID, length, address are added to the transaction, which is complying with the OCP protocol definition. In our specific example, we are always sending an OCP transaction as a response transaction. Thus, we are not making the ID, length, and address field as random, and only we are making the data dynamic array as random. But there is no harm in making all the members as random. You can make it as more general transaction definition. Also, you should implement the new function, the do copy function appropriately to copy the individual members and the convert to string and other functions if you need it at all. At the end, there is a small class called cyclic master ID, which is extending from the sequence item again, and this is implemented to get cyclic random numbers in the environment, because we have to send the transactions with a random ID, but those random IDs should be cyclic in nature. So this is a small technique to generate random cyclic IDs repeatedly in a sequence. But you can ignore if you are not understanding their usage at this point. Next, you will see the implementation of the sequence by using these transactions.